Good afternoon, everybody. We'll get started here shortly. All right, everybody. Thanks for joining in this afternoon. I'm going to go ahead and get started. Let me share my screen. Okay, so here we are in the weekly overviews. And this week, we're dealing with momentum, working energy, and thermodynamics. So on Monday, I talked about momentum. I started talking about working energy, and I said that I would finish that today. Um, Somebody refresh me. Did I talk about the midterm? I think I did, but I'm not recalling whether I did or not. Tyler, Miles, do you recall if I talked about the midterm?
You touched on it, but I don't know how in detail you went.
Okay, I'll do it again just for good measure before we go into working energy, just to make sure that everybody's on the same page. Okay, so my suggestion to you is that you get to the midterm or go to the midterm the same way I'm doing. Notice that I access the midterm through the weekly overview. I know that you will see on your right side menu that midterm exam shows is coming up or in your to-do list. But my suggestion to you is that you go in through the weekly overviews, because there you will find the midterm logistics and the study guide. You won't have access to that if you go in through the to-do list, which some students do, and then they miss out on the opportunity to earn the bonus points. Now I'm it's coming back to me. I did talk about the midterm on Monday, but I'll do it again just to be on the safe side, because I remember talking about the study guide. All right. So the midterm exam logistics basically cover for you, remind you of the deadline, which is this Saturday. Um, it tells you, well, that you will have 2 hours to complete the midterm exam, unless you have, you know, other needs, and that'll be managed on a managed, individually. Um, and it tells you that you can use printed material, including textbooks, formula sheets. So anything you want to have, printed wise, feel free to use that. You can use a calculator. Um, you're not allowed to use a phone, tablet, or any URLs. And I just put that in there, to make sure that we're all operating honestly and fairly when taking this exam. Okay. You have to type your answers, your work in the space provided, and you have to show your work to get credit. If you don't show your work, you will not be given credit, even if your answer is correct. Okay. And if there are any specific instructions with the problem, it will be stated with the problem or with that question. And so you need to make sure that you follow any specific instructions that are given with a question or a problem. Is worth 100 points, and every question has the point values indicated. And roughly 1 week after you complete the exam, I will post a score for you. Okay. And if you miss the midterm exam, um, then you're going to need to provide something official in terms of documentation to arrange for makeup. And examples are listed here, like a doctor's excuse, obituary, judge's order. If you get called out on a extra shift at work, bring a note from your employer on official letterhead, that kind of thing, something that I can verify. Okay. So I do recall covering this on Monday, but again, are there any questions about that? All right. Here's the study guide. So for this study guide, first I list for you the topic areas that are covered. Okay. So, um, and you can see from this, the bulk of this deals with, application of your understanding, right? It's not just definitions or, regurgitating something that you might have read somewhere. It's actually applying the information, that we've been dealing with in these topic areas. So everything, including measurement, scientific method, nature of science, units, unit conversions, 1D motion, projectile motion, circular motion, and vectors. Those are all topic areas that are covered on the midterm. Newton's laws, gravitation, those topics are not covered on the midterm, even though we did cover them last week. Those two topic areas will be picked up on the final exam. Okay. And to complete the study guide, what you need to do is you need to find sources that could be books, internet sites, or other reference sources, and utilize them to create a study guide containing 10 concept facts and 10 problems that you solve relating to these topics. So you should have a total of 20 items on your study guide. 10 of them will be concept facts on these topic areas, and 10 of those items will be problems that you solve related to these areas. Don't use my lecture notes or my extra notes that are in the announcements. And your study guides shouldn't all focus on just one topic. So you should spread it around, right? Make sure you have something dealing with each of these topics.
Can you
Because
repeat that last thing, what they cannot use?
don't use my lecture notes. Okay, because in the weekly overview, my lecture notes say supplemental, right? Can't use my lecture notes to give examples. And in the announcements, I have a link to extra notes for you. You can't use those either. So you have to truly go and find your own sources. Now, under useful links, you will find some things that can help you with this, right? But the goal is to have you.
Example.
Example of what?
Like, I'm kind of confused on what we actually have to do.
So if you go and find a textbook and you go in that textbook and there's a chapter that deals with 1D motion, there will be some concepts regarding 1D motion, right? So for example, if 1D motion was where we started to define what acceleration, velocity, displacement, all those properties were. So if a concept might be, if an object is moving in one dimension, then distance and displacement could have the same magnitude. And then you might give it, show how that could be, right? That's what I mean. So that's a concept. Now, to solve a problem with 1D motion, for example, I might have you might show a sample problem on how you calculate displacement. Does that make sense to you?
Yes, ma'am.
Okay, so you're gonna do 10 concept facts and solve 10 problems. I don't give you those concept facts and problems. You go and find them in whatever sources you like to use. That also means that if you like to use that source, then you might print out some materials from it that you want to have handy during the midterm exam, because you can have printed material available. It also means that since you have been solving problems and answering discussion questions, on these topics for credit in this, towards your grade, I have posted under useful links the solutions to those homeworks and discussions. You could print those out and bring them and have them available when you take the midterm exam. The goal here is for you to compile and utilize whatever materials you feel comfortable using to help with these topic areas while you're taking the exam. The other benefit of building your study guide is that you can turn it in to me by email, and it's worth 10 bonus points toward the midterm. So, my hope is that while you're building this study guide, you'll be reviewing those items, right? And that will help you in your understanding. Okay. So that's the study guide portion. Any questions about that? And thanks, Tyler, for asking that question, because I do get quite a few emails from students saying they're not quite sure what they're supposed to be doing. That's why I like to explain it, and I'm glad you asked questions. All right. So the other item there is the actual midterm exam. So if you click on that, mine looks different because I'm a faculty member, but if I go into student view, this is actually what you see. And so, that the instructions are there again, and then you just hit the take the quiz button, right? And so any questions on how you get to the midterm exam and anything else I've covered in the instructions? All right. So now that's out the way again. I think I've covered it in each class period now. So that's thorough. Just making sure nobody's left out in terms of having an opportunity to ask me questions. All right. So on Monday, as I mentioned, we covered momentum and impulse. And then I started covering work and energy, but I didn't finish it. So my goal is to finish this and then jump right into the thermodynamics material and cover that as well. I do recall that on Monday as well, I talked about the second bonus. So don't forget that you do have opportunity for an additional bonus. My suggestion to you is look at the information in the weekly overview. And then if you can also watch the video from Monday regarding that. And if you have any questions, don't hesitate to reach out to me, because I don't want you to miss out on that opportunity as well. So 20 bonus points are on the table as of right now. All right. So we dealt with work. We talked about the work energy theorem. We looked at the difference between kinetic energy and gravitational potential energy and how the formulas for each one of those. We looked at the idea that, pretty much that work and energy are interchangeable, right? We add in energy into a system so that we can get work out of a system. All right, we talked about the idea of the conservation of mechanical energy. And that is the idea that the total mechanical energy, which is kinetic energy and potential energy, is constant in this closed system, right? Where no external forces can really, well, no, that's momentum, my mistake there. Where in this system, it is closed off, so you don't have the interference of things like friction or these forces where, energy is dissipated out of the system, right? And so when a statement of the conservation of energy can be said to that the kinetic energy and potential energy at the start is equal to the sum of the kinetic energy and potential energy final, right? And so basically what you're saying is that, you know, you can swap the different types of energy around. The energy is interchangeable, but you won't ever have any more or any less energy in the system. And sometimes you hear the conservation of mechanical energy stated that, the conservation of energy stated as, um, energy cannot be created or destroyed. It can only change forms. And I think this is where I left off on Monday. I didn't get a chance to go into details about these non-conservative forces, right? Because I did say that gravity is an example of a conservative force. Because when you do work against gravity, or when gravity does work on an object, it does not matter the endpoint, the path that's taken. Only the endpoints are relevant. And so when we move to looking at non-conservative forces like friction, the work done and the energy utilized in the system is path dependent. Okay. And so they give the example of the baseball player sliding. And when the baseball player's body is in contact with the ground, there's friction. And that friction causes the, ball player, if you could measure, a temperature on his jersey, that's part that's touching the ground, you see that it get warmer, right? Because that energy of motion that the player has, that kinetic energy, gets transformed into thermal energy or heat, and also sound, as the player slides. And so you could think of it like this: if the player is sliding on a shorter or longer path, that's going to impact the amount of thermal energy that is, is created while they're sliding, right? Or the kinetic energy, how much kinetic energy gets converted into thermal energy, not created, because it's the kinetic energy that the player has that quote creates the thermal energy or is converted into thermal energy, right? So non-conservative forces like friction or work, the work done depends on the path taken. And so now the question becomes then, well, how do we account for this work being done by these non-conservative forces? So if we say that, in a system, there are non-conservative forces like friction, how do we account for the work that they do? Well, we can simply think of that. Imagine that system has a way of capturing the energy associated with that friction. And then you could put it back in the system. And so you would have then a way of knowing, how much of the work from the kinetic and potential energy is going to be converted into this work done by non-conservative forces. And so what they're suggesting here is that we just need to have a way to denote the work done by the non-conservative forces, and that they usually write that as a W with an NC. A lot of times you'll see a W with a subscript C to represent the work done by conservative forces like gravity. Okay. And so what we can then do is do a little algebra, manipulate this so that we get a way of expressing the work done by non-conservative forces. And that is the change in kinetic energy plus the change in potential energy. So if we know how much our kinetic energy changes and we know how much our potential energy changes, that difference or that change is equivalent to what's done, the work done by non-conservative forces. Okay. Now, let me just, you know, say to you up front, I'm not interested in having you calculate the work done by non-conservative forces in lecture. You do get into that a bit in lab in the energy experiment that you do, um, you know, utilizing the skate park simulator. But what I am particularly interested in you calculating is the utilization of this statement of the conservation of mechanical energy. And I'll show you what I mean by that here shortly, how I, you know, why I can have you use something simple like this simpler statement where we don't have any friction involved. Okay. And so this is the broadest statement of the law of conservation of energy, because they're not just looking at mechanical energy. You see, in this version of the law of conservation of energy, in this more inclusive version, you see that kinetic energy and potential energy are only just two forms of energy, right? That's what we said, right? Energy cannot be created or destroyed. It can only change forms. And that's why I was kind of trying to be a little bit careful in saying that, you know, the work done by non-conservative forces, that friction energy is created by it's not created, it's because these mechanical energy forms get converted into that, okay, work done by the non-conservative forces. It also says something too that you need to be paying attention here. Notice that this is kinetic energy. This is potential energy. This is some other forms of energy. Could be chemical, could be nuclear, but this is work. And you wonder, when you look at the law of conservation of energy, how does work creep into an equation that deals with energy? And that is because, as I said, work and energy are interchangeable. Efficiency. So this is something that we talk about when we want to look at, you know, the energy conversion process, right? So, you know, how much energy are we putting in and how much work are we getting out, right? How effectively is the energy that we're making available being used to do work, all right? And so the efficiency looks at the ratio of the work out of a system or process divided by the energy in that's put in to that system, okay? And it says here, for real world processes, the work out is always less than the energy in. So there's no 100% energy in equivalent to 100% work out. Not going to happen in the real world. We know that from everyday experience in the real world, there is energy loss and energy and friction involved in almost, you know, all of the processes or systems that we deal with. And so, you know, there's nothing that is 100% efficient in the real world. And so here's a table showing some efficiencies of various activities, devices, and processes. And you can see that, for example, swimming is not a very efficient process. Okay, well, on the surface, right? Um, and then you can see that, for example, an electric motor is an extremely efficient device, 98% efficient. Remember, we're talking about how much energy do we have to put in compared to the work that we get out. And so that will explain, you know, why we want to go to electric motors, right? Electric vehicles, because look at these gasoline and steam engines and even diesel engines. they're not very efficient compared to an electric motor, which is the heart of an electric engine, right? So uh, we're making some strides in that respect, but I guess given the fact that we see some things happening around us in terms of our climate and weather, we need to move a little bit quicker to do what we can, in that respect, to make the transition. All right, power. So here is a new property, power, and that is the rate at which work is done. So when you see that word rate, that suggests that time is involved. And so we're looking at work per unit time. We use the capital P for power. Don't confuse that with the lowercase p that we use for momentum. So power P is equal to work W per unit time. And so because we're dealing with a new property, we got to have our new SI unit. Our new metric unit for power is the watt. Just like your 100-watt light bulbs, for example. How do we break down a watt? 1 watt is equal to 1 joule per second. 1 joule per 1 second. So that means, for example, a 100-watt light bulb is 100 joules per 1 second. Now, be very careful, because when you're solving problems for me and you're asked to give units that, for power, if you use the unit joules per second, I'm going to take points off, because the correct and most complete unit for power is the watt. Okay. And then they show you the relationship between British or English system units, horsepower. That's something that we, especially if you're into like muscle cars or Hemis and things like that, it's something you hear, horsepower, right? And so 1 horsepower is equal to 746 watts. Okay. All right. And so it shows just, some lagniappe here, if you will, that shows how the metabolic rate, because that deals with the energy conversion in humans, right? How effectively is our body converting the food energy into, into a form that is useful to our organs, right? So it shows the power consumed, for example, when the brain is at rest. And well, I wonder, that's pretty a unique statement there, because I wonder, does our brain ever really rest? Even when we're asleep, it seems like something's going on, right? But here, power consumed at rest, 16 watts. Okay. And then they look at that, you see here that gives a metabolic rate, or basal metabolic rate. That's because it's at rest, of 19%. Again, not something I'm interested in having you calculate or anything like that, just informational, right? And then this is one that kind of gives me pause whenever I see it. And that is this world energy consumption. And you can see the trajectory that we're on, right? Because we're somewhere right in here between 2020 and 2025. And we're utilizing on this planet somewhere as around 654 times 10 to the 18 joules uh, you know, which is like, whoa. And you can see, as they mentioned, that the amount consumed, the energy consumed, the demand for energy has doubled since 1990. But, you know, we got a lot more high-tech gadgets right nowadays, right? So I suspect that that's part of it. And then you can see here, um, power consumption in different countries. And I was shocked when I saw this, that we're not number one in this area. Japan is actually beating us quite a bit. I mean, not too bad compared to how much, you know, they're beating other countries, but still, that was eye opener for me that we aren't number one per capita. All right, so that takes care of what I wanted to share with you regarding work and energy. Okay. Yes.
I noticed that Japan's technology and their equipment is and businesses are like they're a lot more.
Yeah,
You
they
know, so that probably what it goes to.
um that could have something to do with it. The reason I said I was shocked. Well, I guess you know, like I shouldn't be, because they're an industrialized country, right? Just like we are, right? You look at some of the, you know, the one that I was, you know, like really interested to see where they were was China, but they have such a large portion of, you know, places and areas where there really isn't much in the way of development. There what is it? You know, they're doing things still in a lot of the same ways they've done them for hundreds of years, right? Where a country like Japan is really like really industrialized. And you can see that most of the countries listed in toward the top are more industrialized countries. All right. So back into the weekly overviews, and we got thermodynamics to deal with. Okay. Now I'm gonna try to focus on the areas where I think you'll have opportunity to calculate things and focus on those formulas. A good bit of this material is, you know, is something that you can read and digest, but I like to have an opportunity to look at a couple of problems on this topic. And so, you know, some areas of my notes, I'll just point out that, okay, you can just read and review this, but give more emphasis to those areas where you will have to, you know, engage in utilization of formulas or so on. Okay. All right. So, you know, activities. You got some things on your plate here. Um, boy, your last bonus. Okay. I tell you what I'm gonna do. I'll come back and I will put this last bonus. I'll put this in next week's material to give you a little bit more time to deal with it. Okay. You don't have to turn that in on Saturday as well. You got enough things due on Saturday and your midterm. So I'll put the last bonus. I'll move it. Okay, so don't worry about that last bonus right now. I'll move it and I'll talk about it next week. All right. So your thermodynamics discussion and problem set number 10 are due this Saturday. And so here are the materials that relate to this topic that I made available to you. Your book, the chapter 19 in the textbook deals with thermodynamics. There's some videos. There's a great NASA website on thermodynamics that I've shared with you that you'll want to take a look at. And so these 3 packets are my notes. But again, uh, some of them have areas where we can just kind of skim over, okay? I put this information on temperature in here so you can have a general definition of temperature and understand its relationship to um, kinetic energy, because that's a property that we've investigated. And I wanted you to see that temperature has a direct connection to um, energy. So again, this material is something that you can read through. Um, they talk about the various temperature scales, and you want to focus on that. But as far as like converting from one temperature scale to another, um, you can just use a unit converter to do that. You don't have to, even when you're doing the homework that relates to this, you can just use the unit conversion tool, because we've talked about converting. And so we don't need to spend time converting from Celsius to Fahrenheit. Just if you need to convert, use the unit converter. It's right under useful links. You have access to it. All right. So a lot of this is just good information. I do want to say just a few things about the absolute zero scale. That is the Kelvin scale. And the Kelvin scale is what we utilize in physics and physical science because it is not dependent upon atmospheric pressure the way our Fahrenheit and Celsius scales are. Okay, the Celsius and Fahrenheit temperature scales are based on water, and the boiling point and freezing point of water can change as atmospheric pressure changes. But the Kelvin scale, which is remember, the Kelvin scale is your standard, right? It is your base property unit for temperature in the SI system. So the SI unit for temperature is Kelvin. So this scale is the one that we primarily focus on, and that is because this scale is based on gases, right? The behavior of gases. In fact, this has a connection to the idea of an ideal gas, which is a construct, because in the real world, there's no gas is perfect or ideal, but all gases have behavior such that when you look at how their temperature decreases when you maintain maintain a constant volume of that gas, and the temperature begins to decrease because you look at the pressure as well. You get down to a point where all of them extrapolate to this temperature of 273.15 degrees Celsius. And that is designated as absolute zero. So that is the lowest temperature possible. That is the temperature at which all molecular motion ceases. So temperature is related to kinetic energy. If all molecular motion ceases, then the kinetic energy is zero because nothing's moving, right? And so that temperature is designated as absolute zero, or the equivalent of 273.15 Celsius, okay? And so they tell you here, because the number of physical quantities such as the volume of an ideal gas, right? Remember, ideal means it doesn't really exist, but we get close. So the volume of an ideal gas is directly related to this absolute temperature. Um, and so the Kelvin scale, by the way, we don't say degrees Kelvin, we just say Kelvin. Um, the Kelvin scale has its starting point at 0 Kelvin, okay? All right. You can look at the zeroth law of thermodynamics. It's very easily stated that if things are at the same temperature, they're in thermodynamic equilibrium. That's easy enough. If they're at the same temperature, they're in thermodynamic equilibrium. Think of it this way. If I have hot water and cold water, if I mix them, eventually they'll settle down to the same temperature. Okay. And so it'll be stable, meaning the temperature is not going to go up or down anymore. It's at equilibrium, balanced. We don't deal with linear expansion, so don't worry about those. It's worth noting that, you know, the ideal gas law looks at pressure, volume, and temperature. You don't have to solve any kinds of problems dealing with the ideal gas law. I just wanted you to understand that we can study the behavior of real gases by utilizing this construct of an ideal gas. And when we utilize this construct of an ideal gas, there's a relationship between the pressure, volume, and temperature. Again, you're not solving any problems with that, just understanding that there's a connection between the Kelvin scale and ideal gas behavior. We definitely don't do Avogadro's number. That's a chemistry thing all day long. That's beyond our requirement here. And kinetic theory, we don't go there either. So, yeah, that's pretty much that. There are 3 temperature scales: Celsius, Fahrenheit, Kelvin. We focus on the Kelvin scale. If you need to convert, use a unit converter. Bam, there's temperature. All right, heat. Now this is where we will look at a couple of sample problems here shortly. So again, I'm gonna go through this and focus on the areas where you are most likely to have to do some type of calculating, okay? And so first things first, we gotta know what heat is. We understand temperature, you know, from the perspective of we can measure the amount of kinetic energy that a substance has by measuring its temperature. But a lot of times people use the words temperature and heat to mean the same thing, and they don't, okay? Heat involves a transfer of energy because of a temperature difference, okay? So the temperature of an object is a measure of the average kinetic energy of its atoms. Heat, by comparison, represents the thermal energy of the object. Now, let me break that down for you. Temperature focuses on kinetic energy. Heat focuses on thermal energy, which is a combination of kinetic energy and potential energy. And you might be wondering, how do we look at potential energy for atoms and molecules when we look at the spacing between atoms and molecules? Okay, that spacing is what creates that stored energy, whether they're repelling or attracting. Okay, so they give a really good example here. So let's say you had a glass full of water and a swimming pool full of water, and they're both at the same temperature. That could happen, right? You could have a glass of water and a big swimming pool of water, and they be at the same temperature, okay? But the swimming pool is going to have a whole lot more thermal energy, heat, than the glass. Why? Because you have more of it, right? So that's a good way of understanding the difference between the two. If you have different amounts of the same substance at the same temperature, you'll have more thermal energy in the one you have more of, okay?
I'm sorry, can you repeat the last statement?
Sure, no problem. So if you have the same substance, okay, same temperature, but in one situation you have more of it, more mass, then you will have more thermal energy in the one you have more of. And that's why they give the example of the swimming pool. They're both holding water, same substance. They're both at the same temperature. Let's say a nice 85 degrees Fahrenheit. But the swimming pool has a whole lot more water than the glass. So the swimming pool will have more thermal energy. Okay? So that really does give a good illustration of the difference between temperature and heat. I like to think of heat as energy. You can kind of think of energy associated with um, temperature changing, because heat flows from a hot object to a cold object. That help to make that clear for you? Okay.
Yes.
Now this is they talk about the idea of the mechanical equivalent of heat, meaning that you can utilize motion to generate heat. Okay. And so for example, if you take something and stir, so you're physically doing a stirring motion, right? So you're moving, that's mechanical. And as you stir, like let's say, for example, you have a liquid in a glass. As you stir that liquid, then you will heat, you could change, you could heat it up, as we'll say. Okay, you can see the temperature going up. Okay, and so that's a nice thing you see at some of the children's museums where they get on the bike, they pedal, and so that's mechanical, right? That's mechanical energy, because that's energy of motion. And while they're paddling the bike, that bike is attached to a set of paddles that turn in this big bucket of water. And there's a thermometer in that bucket. And the more they paddle, the higher the thermometer goes. Okay. So that's taking your physical work and converting it into heat energy. Okay. And you see there, this equivalence is named after joule. Remember, our unit of work, our unit of energy, our unit of heat are all three joules. Why? Because work, heat, and energy are interchangeable. They talk about units for heat. We focus on joules. We don't really focus on calories. Although I know that, that is very useful for like when you're dealing with nutrition and food and biological processes, as we just saw in the previous set of information. But you know, the ideal power consumption, for example. But we don't really focus on calories here. We focus on joules. Okay. Now here we get to something where there's a potential for having to do some calculations, because now we know what heat is. The question is how much heat is transferred, right? We said that heat involves a transfer of energy when there's a temperature difference, right? Heat flowing from a hotter object to a colder object until they stabilize and get to thermal equilibrium. Well, the question is, how do we figure out the amount of heat that's going to be transferred? And we can use that, the heat capacity formula. The formula that you see in the box is the heat capacity formula. And so in this equation, we're using Q to represent heat, okay? M is the mass of the substance. That's why I gave the example of the glass of water in the swimming pool, because the mass affects the amount of heat. The delta T in the formula represents the temperature difference, delta T. So we know how to find delta. It means we take what? The final value minus the starting value. And we'll see that when we solve look at a couple of sample problems here shortly. Now, the only question is the C that's in the middle. The C that's in the middle is the specific heat. Now, specific heat is a property of a substance, okay? Just like every material has a density, every material has a specific heat. And that specific heat is found in tables. You look it up. It's material dependent. You look it up in tables, okay? So if I want you to solve problems using specific heat, I got to give you the specific heat of the material, because I don't expect you to memorize it, okay? And what that specific heat, that value C, what it tells us is how easy or how difficult it is to heat up or cool down a substance, okay? And they give like a formalized definition here, but I'm just trying to give you a definition that's easily understood. Objects that have a bigger value of C are more difficult to heat up and they take longer to cool down. Materials with a small value of C are easy to heat up and they cool down very quickly once they're you know, not in the presence of a heat source, okay? So I'll give you an example. Water has a very high specific heat, 4,184 joules per kilogram Kelvin, okay? And so because water has a high value, one of the higher values of specific heat, we say that water is very heat intensive because it takes a lot of energy to heat up water. And once water is hot or warm, it stores or holds its heat very well. So it takes a lot of energy to heat it up, and you have to take out a lot of energy to cool it down. Silver, on the other hand, is a material with one of the lower values of specific heat. So it's like 200 and something. So it means that silver is very easy to heat up, and So you don't have to expend a lot of energy to heat it up. And once you remove heat from it, you can cool it down very easy. Okay, so it'd be great if we had pots made of silver for cooking, but of course they'd be way too expensive, because let's say for example you want to fry your eggs in the morning. A silver pot would heat up real quick, fry your egg really quick. As soon as you turn off the fire, it'll cool down and it won't continue to cook and scorch your eggs. An aluminum pot, on the other hand, or I like to call them Magnalite pots because it's like a combination of metals. A Magnalite pot would be terrible for frying, because it would take a lot more heat to heat up that Magnalite pot. And once it's hot, it'll continue to cook your egg even after you turn the fire off. But that Magnalite pot would be great to cook gumbo in. Why? Because once you get it good and hot, you can turn the fire down and it'll just cause your gumbo to just be on a nice simmer, because the pot it'll hold this heat real good. Okay? So specific heat. All right? So now we'll see how to utilize this formula here in an example that I want to share with you. So bear with me. I'm going to go into the announcements, and this will kind of remind you of a resource that you have at your disposal, that you have had at your disposal for the entire course. I put this out there. And so if you click on this link, again, this is in the announcements. Notice there's a folder for every topic that we cover, right? And so I'm going to go in the temperature and heat notes. Okay. And I'm going to go into this example here. So this is an example of heat transfer. Okay. So it says here, how much heat must be added to 1 kilogram of copper to raise its temperature from 20 degrees Celsius to 100 degrees Celsius. Okay. So we're dealing with copper. So we got to go look up in a table CP for copper. So I gave it here, 0.386 kilojoules per kilogram Kelvin. That's the specific heat value for copper. Pretty small value. Copper is the next best thing to silver for cooking. That's why you have copper bottom pots. Okay. This also explains why it's used in a lot of like wires, like plugs and cable wires, because of its specific heat value. Makes it it affects its conductivity as well. Okay. So now this copper is being raised from a starting temperature of 20 degrees Celsius to a final temperature of 100 degrees Celsius. And so we can get our delta T by doing TF minus TI. And then they gave us the mass of the copper, 1 kilogram. Okay. And so the mass is 1 kilogram. The temperature difference is 80 degrees Celsius. But hey, wait a minute. My CP value doesn't use Celsius, it uses Kelvin. So you might be saying, well, hey, don't I have to go and calculate this temperature difference in Kelvin? If the temperature difference is 80 degrees Celsius, that is equivalent to 80 Kelvin. Notice the temperature difference is the same on the Celsius scale or the Fahrenheit scale. So here we're changing the temperature, raising the temperature by 80 degrees Celsius. We are also raising the temperature 80 Kelvin, because the temperature difference is equivalent on either scale. Okay. So now all we have to do then is multiply that by our value for CP, which is 0.386 kilojoules per kilogram Kelvin. Again, this value came from a table. I don't ever expect you to memorize CP values. I would give you whatever material dependent constants you need. Okay. So now when you multiply that out, you get 30.88 kilojoules. 1 times 80 times 0.386, 30.88. Notice my kilograms cancel, my Kelvin cancels. I'm left with kilojoules. Okay. So in order to raise the temperature of that copper by 80 degrees, I need to put in almost 31,000 joules of energy. Okay. Any questions on that example? All right. I'm going to show you a couple of more examples. So this is a great, see, they got a nice little table in this one. Not that I wouldn't, I expect you, I mean, to, you know, have known that, or because again, I'll give you whatever table you need. Okay. And you see the nice thing is here, I can see some of the different values of specific heat for different materials. Right. So here's an example. A 32-gram silver spoon cools from 60 degrees Celsius to 20 degrees Celsius. How much heat is lost by the spoon? Now, this is a very important example because it shows you that in the end, Q can be negative. If you're taking out heat and dropping the temperature, your final temperature is going to be smaller. So when you subtract, you're going to get a negative. Okay. So now we have our mass given 32 grams, but hey, wait, our formula requires the mass to always be in kilograms. So that's why I have to convert 32 grams to 0.032 kilograms. So if I divide 32 by 1,000, then I get 0.032 kilograms. Okay. My temperature difference, 20 degrees Celsius minus 60 degrees Celsius. That's minus 40 degrees Celsius temperature drop. That is a minus 40 Kelvin temperature drop. Because remember, the temperature difference is the same on either scale. So now substitute your mass, your temperature difference, and CP for silver, which I pulled from the table, 235 joules per kilogram Kelvin. Okay, so it doesn't matter if you are solving the answer and getting it in kilojoules or joules. That is, I mean, that's, you know, potato, right? As long as you set it up and solve correctly for the values that you are given, that's what matters. Okay. So if CP is written using joules, then your answer will be in joules. If CP is written in kilojoules, your answer will be in kilojoules. That doesn't matter. Okay. So when I multiply 0.032 times negative 40 times 235, I get negative 301. My kilograms will cancel. My Kelvin, my temperature will cancel, right? Because the temperature difference is the same on either scale. And so I will be left with joules as my unit, which is the unit for heat. Okay, so whenever you are removing heat, your Q has to be negative. Whenever you are putting in heat, your Q has to be positive. All right. So I want to spend the remaining time looking at heat associated with, so this focuses on this, see, that's a table there with specific heat values for different materials. Their table doesn't have water on it, even though that's, you know, a very important property. They do have ice, but even ice is not as heat intensive as liquid water. The other heat transfer process that I want to focus on is the latent heat that is associated with the phase change. So there are three phases of matter: solid, liquid, gas, that we care about. There's plasma, but we don't really focus on that. Solid, liquid, gas. And whenever a substance is undergoing a phase change, then the temperature is not going to change. So when a material is changing its phase, its temperature is not going to change. So since its temperature will not change, we can't use our specific heat formula. We have to go to what's called the latent heat formula. Latent heat refers to the amount of heat that is absorbed or released when a material changes phase. And so here is the formula that we use whenever a substance is undergoing a phase change. Q equals mL. And L is what we call the latent heat coefficient. The latent heat coefficient is material dependent. You have to look up the value in tables. So if you need to use the latent heat coefficient L, I will give you the value. You just need to be aware that L has two flavors. L can be associated with vaporization processes, LV, or freezing or fusion properties, transitions, I should say, LF. So when you look up the latent heat coefficient for a substance, you will see two values indicated: LF for transitions around that material's freezing point, and LV for transitions around that material's vapor or boiling point. Okay? And so what I want to do now is I want to take a look at an example that utilizes LL, this latent heat process. Okay? So I'm going to go back into my extra notes, and there's some nice examples worked for you here. Let me go to it. So let me blow that up a little bit. So you have all these great notes and examples in here. And if you aren't taking a look at this stuff and utilizing it, you're kind of missing out on some great things that can help you. All right. So I'm going to go right into this example that deals with our latent heat formula. You can see it here highlighted on the screen, Q equals mL. So it asks the question, how much heat must be removed from 1 kilogram of steam at 150 degrees Celsius to convert it to 1 kilogram of ice at 0 degrees Celsius? So we got this really hot steam, and we want to take out enough heat to get it all the way down to ice at 0 degrees Celsius. Now think about what's happening here. We are changing the temperature because we're going all the way from 150 degrees Celsius all the way down to 0 degrees Celsius. But we're also changing the phase because we're going from steam all the way down to ice. And so this is an example where you have to utilize both processes. You have to use the processes that looks at heat capacity, where the temperature is changing, and latent heat, where the phase is changing. Okay, and so I've worked this example for you. here. So I put the first two steps on this slide. And I do apologize. I'm terrible at taking photos. And so the first part of my screen is a little bit blurry, but I think you can make it out. So the first step that we're gonna do is we have this 150-degree steam. We gotta cool this steam down. We gotta cool this steam down all the way to 100 degrees Celsius. And the reason we stop at 100 degrees Celsius is because that is the boiling point, for water. 100 degrees Celsius is the boiling point for water. So now let's solve. We have to use our heat capacity formula. How do I know that? Because the temperature is changing. Remember, you can change the temperature or you can change the phase. You can't do both at the same time. Okay? Q equals mCp delta T. So they gave me the mass as 1 kilogram. They also gave me CP for steam. If you looked at carefully at the description of the problem, just below the description, they gave you the specific heat values for the substances you were using. So CP for steam is 2 kilojoules per kilogram Kelvin. How much are we dropping the temperature? By 50 degrees Kelvin. Okay. Well, 50 Kelvin. I shouldn't say degrees. That's bad language, right? We're dropping it 50 Kelvin. All right. So when we multiply here, we get 1 times 2 times negative 50, negative 100 kilojoules. So to change this steam that's at 150 degrees Celsius to steam at 100 degrees Celsius, we have to remove 100 kilojoules of heat. Okay. Step number 2. Now we're starting off with steam at 100 degrees Celsius. But what I can do is change the phase so that it's liquid at 100 degrees Celsius. Okay. So notice, while the phase is changing, the temperature stays fixed at 100 degrees Celsius. So the temperature change is 0. What happens if I put a temperature change of 0 in this formula? The whole formula goes to 0. That's why I can't use it when there's a phase change. So I have to use the formula Q equals MLV. Why am I using LV? Because I'm dealing with the boiling point or the vapor point. So let's multiply. The mass is still 1 kilogram. And it gave me the LV value for transitioning between steam and liquid. And that is 2,260 kilojoules for every kilogram. Now, if I multiply 1 times 2,260, I don't get a negative number. But because I am, again, removing heat, I have to provide the negative sign here. This formula is not going to come out negative. This formula will automatically come out negative if you're dropping the temperature. But the latent heat formula will not come out negative on its own. If you are removing heat, and you do have to remove heat to convert steam to a liquid, right? It's condensing, right? If you're condensing this steam into a liquid, you have to remove heat, so you must provide the negative sign. Otherwise, this is going to come out positive, and you'll be telling me that I can put in heat and change steam to liquid. All right. And then steps 3 through 4. Steps 3 through 4. In this third step, step number 3, I'm going to take that liquid that's at 100 degrees Celsius, and I'm going to cool it all the way down to liquid at 0 degrees Celsius. So in this case, I'm not changing the phase, but I am changing the temperature. So I need to go back to my specific heat formula. Plug in my mass. They gave me the specific heat for liquid water. And I'm dropping the temperature by 100 Kelvin. Because I'm going from 100 to 0. So when I multiply that out, because the negative sign is in the delta T, I get a negative sign here. Negative 420 kilojoules. So to change the temperature of this liquid, I got to pull out an additional 420 kilojoules of energy or heat. And then your final step 4, oh, sorry, I mean to do that. My bad. I was trying to scroll. There we go. My final step 4, I have a liquid that's at 0 degrees Celsius, but I have to transition that to an ice at 0 degrees Celsius. So I go to my latent heat formula because what? My temperature is not changing, but my phase is changing. So now the mass is 1 kilogram again, and they gave me LF. Why do I need LF? Because I'm dealing with the freezing point. So plug in 334 kilojoules per kilogram, which is given, right? When you multiply that, you get 334 kilojoules. But again, you have to provide the minus sign here because you know you're removing heat. Okay? If you're putting in heat, everything's going to come out positive like it should. But if you're removing heat, the latent heat formula does not come out negative on its own. You must provide the negative sign. So now to know the total amount of heat that we have to remove to take this steam that's at 150 degrees Celsius all the way down to ice at 0 degrees Celsius, we add up the Q values for each of these 4 steps. And that will tell us how much heat to remove. Okay? So that's an example of utilizing the heat transfer formula for changing the temperature or changing the phase, right? The only thing left that I have not looked at, and then there's a lot more information in these remaining slides that you can look through. We don't deal with rate of cooling. If the examples that I've worked here regarding heat are the kinds of examples you should be able to work. We're not looking at transfer, the cooling rate or conduction rate. But they give a lot of just examples and definitions of methods of heat transfer, and you can take a look at that and read it. We don't, again, we're not getting into the rate of transfer by radiation. Where that's a bit above what we want to do in here. So just the heat transfer for changing the temperature with specific heat and heat transfer due to a phase change, latent heat, right? And then the thermodynamics notes. So they talk about all of the different laws of thermodynamics. The only one you have to focus on is this first one. The first one is the one that I focus on the most. It's okay if you read and know about the others, but the first law of thermodynamics is what I'm interested in. Why? Because the first law looks at the relationship between work W, heat Q, and energy delta U. They're using, instead of E for energy here, they're using U, and they're using delta U to represent the change in the internal energy. So what does this first law say? That the difference between the heat that you put in and the work that you get out is how much the internal energy changes. Okay. So you put in heat Q, you get out work W. The difference between the two is delta U. And basically the first law says that Q and W will not be equal. So delta U will not be zero. The first law says that Q and W will not be equal. You will always get out less work than the energy you put in, the heat that you put in. So there's no 100% efficiency here. Okay. So you put in heat, the system does some work. You never get 100% efficiency, so you can never get all of the work one for one for the heat that you put in. Always get out less work. Something always gets wasted. Or another way to say that is it gets used up in the internals of the system. Okay. First law of thermodynamics. The other laws of thermodynamics, you can read about them, but this is the one that you need to focus on. And this is the one that you'll practice with in your discussions and in your problem set. Okay. So that's what I wanted to share with you today. I do recognize that it's quite a bit. That's why I tried to be a little bit more focused in, in terms of the thermodynamics. So that you would have what you need to tackle the assignments. And I will say this too, if you're working at any point on any of these areas, momentum, working energy, or thermodynamics, please don't hesitate to reach out to me with your questions. All right. So I'm a little bit over. I do apologize. I thank you for indulging me. If you have questions, hang around. I'm happy to answer them. If not, we're done for today. Okay, so that silence tells me that everybody's good. So I'm going to stop the share and end the recording.